Some locomotives were designed to revolutionize railroading. They promised unprecedented power and cutting-edge technology, and they failed miserably. From turbines that could not keep up, to duplex drives that slipped at the worst moments, here are 15 innovative steam engines from the 1940s that promised the future and delivered disaster. Number 15. Baltimore and Ohio. N1, George H. Emerson. In 1937, the Baltimore and Ohio built what they called the future of American steam power. The N1 was the first duplex locomotive ever constructed, featuring a 4-4-4-4 wheel arrangement that split the driving wheels into two groups powered by separate cylinders. The idea seemed brilliant on paper. Smaller cylinders meant less reciprocating weight and smoother operation at high speeds. The locomotive could theoretically run faster and more efficiently than anything else on rails. But here is where it went wrong. The rear cylinders sat right beside the firebox, and firebox temperatures exceeded 2,000 degrees. The heat cooked the rear cylinders constantly. Lubricants broke down within hours. Metal expanded unevenly. Wear rates on those rear cylinders ran triple what anyone expected. Mechanics spent more time replacing seals and pistons than they did on any other locomotive in the fleet. The placement also limited the firebox size, strangling the very power output the design was supposed to improve. Baltimore and Ohio tested it extensively, but every solution created new problems. By 1943, they gave up and retired the N1 after just 6 years of troubled service. The locomotive that was supposed to pioneer a new era instead became a cautionary tale. The London and North Eastern Railway wanted something revolutionary in 1929, and they got it. The W1 arrived with a water tube boiler operating at 450 pounds per square inch, nearly 3 times the pressure of conventional locomotives. Engineers wrapped the whole thing in a streamlined casing and kept the project so secret that workers nicknamed it Hush Hush. The higher pressure was supposed to mean more power from less fuel. But high pressure brought high problems. The boiler's narrow tubes scaled up constantly, requiring weekly cleaning that took locomotives out of service for days. Water quality had to be perfect, and perfect water did not exist on British railways. Even worse, the vibration from the high-pressure system cracked welds and loosened fittings. Maintenance crews reported finding new leaks after almost every run. The W1 spent more time in workshops than on the main line, and when it did run, fuel consumption was no better than standard locomotives. By 1937, the London and North Eastern Railway admitted defeat and rebuilt it with a conventional boiler. The streamlined shell remained, now hiding ordinary technology underneath. The grand experiment in high-pressure steam had produced exactly nothing useful, except proof that some innovations simply are not worth the trouble. Number 13. Pennsylvania Railroad Q1. In 1942, the Pennsylvania Railroad built the Q1, a 4644 duplex that looked like something from a science fiction film. The streamlined shroud covered a locomotive designed to haul heavy freight at passenger train speeds. It was supposed to combine the power of a freight engine with the speed of a passenger locomotive. But the Q1 had an unusual problem. Its rear cylinders faced backwards, exhausting toward the tender instead of toward the front. This meant the exhaust could not help draft the fire the way it did on conventional locomotives. The boiler had to work harder to maintain steam pressure, especially when climbing grades. Then there was the heat issue again. Like the B&O N1, those rear cylinders sat right beside the firebox. Temperatures warped cylinder castings and destroyed lubrication. Pennsylvania railroad shops reported replacing rear cylinder components at 5 times the rate of front components. The streamlining itself became a liability, trapping heat inside the shell and making maintenance access a nightmare. Workers had to remove panels to reach anything, turning simple repairs into hour-long ordeals. Only one Q1 was ever built, and it ran just 165,000 miles before the Pennsylvania Railroad scrapped it in 1946. 4 years of service from millions in development. Number 12. Union Pacific Steam Turbine Locomotives. In 1938, General Electric convinced Union Pacific to try something radical: steam turbine electric locomotives. Instead of pistons driving wheels, a coal-fired boiler would make steam that spun turbines, which powered electric motors on the wheels. General Electric delivered two massive units that looked more like power plants than locomotives. The technology worked, technically. The turbines spun, the motors turned, the wheels moved, but the boilers could not keep up. Turbines need consistent, high-volume steam, and conventional locomotive boilers were designed for the pulsing demands of reciprocating engines. At low speeds, the turbines worked fine. At high speeds, steam pressure dropped and power evaporated. The locomotives that were supposed to revolutionize mainline railroading could not maintain speed on the very grades Union Pacific needed them for most. Water consumption was astronomical because the turbines exhausted steam faster than boilers could make it. Coal consumption followed suit. By 1939, less than a year after delivery, Union Pacific sidelined both units. They were scrapped in 1943. General Electric would try again with other railroads, but the fundamental problem remained. Locomotive boilers were not turbine boilers, and nobody wanted to redesign everything from scratch. Oliver Bullide was a genius who did not know when to stop. In 1949, his leader class represented everything he believed about steam's future: fully enclosed like a diesel, double-ended so it never needed turning, and powered by sleeve valves instead of traditional piston valves. The design looked revolutionary. The reality was absolutely unbearable. The enclosed body turned the engine room into an oven. Crews reported temperatures exceeding 140 degrees inside the casing. The fireman worked in a compartment that was essentially a mobile sauna, sometimes with flames licking through gaps in the firebox cladding. One test crew member collapsed from heat exhaustion during trials. The sleeve valves, Bullide's pride, proved almost impossible to lubricate properly. They seized up constantly, sometimes stranding trains mid-journey. The chain drive that connected the engines to the wheels stretched and wore unpredictably. Timing would drift, causing rough running and mysterious power losses that baffled mechanics. British Railways spent nearly £500,000 on 5-litre locomotives. Only one ever ran under its own power, and that one failed repeatedly during testing. By 1951, they cut their losses and scrapped everything. Bullide left for Ireland, where he tried again. The Pennsylvania Railroad S1 of 1939 was engineering excess made real. At 140 feet long, with a 6-4-4-6 wheel arrangement, it was the largest rigid-frame locomotive ever built for passenger service. Raymond Loewy designed the streamlined shell, creating something that looked like it belonged in the 23rd century. It was supposed to pull the Broadway Limited at speeds exceeding 100 miles per hour. But the S1 belonged nowhere on the Pennsylvania Railroad's actual system. It was too long to fit on turntables. It was too heavy for most bridges. It could not navigate the tight curves in terminals without derailing. The Pennsylvania Railroad had essentially built a locomotive that could only operate on a tiny fraction of its own main line. Even there, problems multiplied. The duplex drive meant 4 cylinders instead of 2, and the front and rear drivers never seemed to work together properly. When starting, the wheels would slip violently. Engineers learned to nurse the throttle with surgical precision, and even then wheel slip could stall trains on grades that older locomotives handled routinely. The S1 spent most of its career on display at the 1939 World's Fair, where it looked magnificent and did not have to actually work. By 1946, the Pennsylvania Railroad gave up and scrapped its showcase locomotive. Number 9. Pennsylvania Railroad S2. The S2 of 1944 represented the Pennsylvania Railroad's attempt at steam turbine technology without the complexity of electrical transmission. Instead of turbines driving generators, driving motors, the S2 used direct mechanical drive from a massive turbine to the wheels. The concept was simpler in theory. In practice, it was a disaster waiting to happen. Turbines hate changing speeds. They want to spin at constant RPM, but locomotives need to accelerate, decelerate, and crawl through yards. The S2's turbine was optimized for about 100 miles per hour. At that speed, it was remarkably efficient, using less coal per ton-mile than any reciprocating locomotive the Pennsylvania Railroad owned. Below 30 miles per hour, it was catastrophically wasteful, consuming steam faster than the boiler could make it. The reverse turbine needed for backing up added weight and complexity, while being used perhaps 2% of the time. Every yard movement cost a fortune in fuel. The Pennsylvania Railroad tested the S2 extensively, trying to find ways to make turbine drive work for railroad service. They never solved the low-speed efficiency problem. By 1952, they scrapped the S2 and abandoned direct turbine drive entirely. The locomotive that could have been revolutionary at constant high speed could not survive in a world that demanded flexibility. Number 8. Chesapeake and Ohio M1. The Chesapeake and Ohio M1 of 1947 stretched 154 feet from pilot to tender, making it among the largest steam locomotives ever built. Like Union Pacific's earlier turbines, it used steam turbine electric technology, generating electricity to power traction motors. Unlike Union Pacific's units, the M1 was supposed to actually work. It did not work at all. The M1's boiler was larger and more powerful than anything General Electric had tried before. It made plenty of steam. But coal dust and ash, the constant companions of steam power, found their way into the turbines. The delicate blades that spun at thousands of revolutions per minute could not tolerate particles grinding against them. Efficiency dropped within hours of each cleaning. Cooling systems for the generators struggled to handle the heat. Electrical failures became routine. Chesapeake and Ohio ordered 3 M1 units, expecting them to revolutionize coal transport. Instead, they spent more time in shops than on the road. Not one completed a single run without some failure requiring attention. The crews called them white elephants and dreaded assignments on them. By 1950, Chesapeake and Ohio surrendered and scrapped all 3 units. The future belonged to diesel, not steam turbines. Number 7. Pennsylvania Railroad Q2. The Q2 was supposed to be everything the other Pennsylvania Railroad duplexes were not. When it arrived in 1944, it was the most powerful non-articulated locomotive ever built, producing nearly 8,000 horsepower on the test plant at Altoona. The 4-4-6-4 wheel arrangement fixed the backward cylinder problem that plagued the Q1. The Q2 could pull 125 freight cars at 50 miles per hour. On paper, it was the ultimate freight locomotive. But here's the thing. The Pennsylvania Railroad speed limit for freight trains was 50 miles per hour. The Q2's power advantage over conventional locomotives only appeared at higher speeds. Below the limit, it performed about the same as the much simpler J1 Class 210-4s. Same tonnage, same speed, but with twice as many cylinders to maintain and far higher operating costs. Shop records showed intermediate maintenance on a Q2 cost over $30,000 compared to less than $20,000 for a J1. The automatic slip control mechanism added complexity without solving the fundamental duplex problem. When dieselization came, the Q2s were obvious first targets. They cost more to run than simpler steam locomotives and could not match diesel efficiency. All 26 were gone by 1951, just 6 years after the class was complete. The most powerful rigid-frame steam locomotive ever built was also one of the shortest lived. Number 6. Norfolk and Western Jawn Henry. The Norfolk and Western was the last Class 1 railroad still building steam locomotives when they ordered the Jawn Henry in 1954. Named after the legendary steel driver who raced a machine and died, the name proved tragically prophetic. This steam turbine electric was supposed to prove that steam could still compete with diesel power. At 161 feet, it was the longest steam locomotive ever built. It could not fit on any of Norfolk and Western's turntables. It could not even turn around without special arrangements at specific locations. The Babcock and Wilcox water tube boiler operated at 600 pounds per square inch, twice the pressure of conventional locomotives. It was supposed to deliver more power from less fuel. Instead, the automatic controls that managed that pressure proved temperamental at best. Coal dust and water infiltrated the electrical systems, just as they had on every other turbine electric. The traction motors failed repeatedly. But the real tragedy was the comparison. Norfolk and Western's own Class A 2664s and Y6B 2882s, designed in Roanoke's own shops, outperformed the Jawn Henry in actual service, while being far easier to maintain. The railroad that built some of the finest steam locomotives in America could not make the turbine work. They scrapped it in 1957. The two T1 prototypes of 1942 were promising. Powerful, fast, and capable of sustained high-speed running, they proved the duplex concept could work for passenger service. So the Pennsylvania Railroad ordered 50 more in 1945 without solving the prototype's problems first. That decision haunted them for years. The production. T1 locomotives arrived in 1945 and 1946 with poppet valves that were nearly impossible to maintain properly. The Franklin Type A oscillating cam valve gear was so complex that many shop workers never fully understood it. Key components were hard to access during overhauls. When valves needed adjustment, which was constantly, mechanics had to disassemble major portions of the locomotive. But the wheel slip was worse. The T1 was phenomenally powerful, and engineers who had learned on conventional locomotives opened the throttle too fast. The wheels would spin violently, sometimes at high speed. The divided drive meant each engine set could slip independently, creating chaos. Norfolk and Western tested one and found its sanders bent, so the sand missed the rails entirely. If the Pennsylvania railroad shops could not maintain them properly, what hope did they have? By 1949, most T1 locomotives sat in storage. The locomotive that was supposed to save steam passenger service instead proved that complexity without reliability means nothing. The United States was not the only country chasing steam turbine dreams. In 1946, the newly formed SNCF in France commissioned a steam turbine locomotive that would push the technology further than anyone had tried. The 232 U1 used a Velox boiler operating at 870 pounds per square inch, the highest pressure ever attempted in a production locomotive. The turbine drove the wheels through a complex mechanical transmission, including a hydraulic coupling. It was supposed to combine European precision with American power. Instead, it combined their worst problems. The Velox boiler required absolutely pure water. French water supplies could not deliver. Scale formed constantly, blocking the narrow tubes and reducing efficiency within days of each cleaning. The mechanical transmission that connected turbine to wheels wore out at alarming rates. Gear teeth stripped, bearings failed. The hydraulic coupling leaked. SNCF engineers worked on the 232 U1 for 3 years, trying to make it reliable enough for regular service. They never succeeded. The locomotive spent more time in shops than on tracks. It ran test trains and demonstration runs, but never achieved the sustained service its designers envisioned. By 1949, SNCF abandoned the project. Europe's most ambitious steam turbine experiment joined America's in the scrapyard. Number 3. New York Central Niagara class problems. The New York Central Niagara was not a failed design. It was one of the finest conventional steam locomotives ever built. But it represents a different kind of failure, the failure of perfection to matter. The S1B Niagaras arrived in 1945 and 1946, just as dieselization accelerated. They were everything a steam locomotive should be: powerful, efficient, reliable, and capable of sustained high-speed running. Test data showed them matching or exceeding diesel performance on every metric except one: maintenance costs. And that one metric killed them. The railroad calculated that a Niagara required 1.5 hours of maintenance for every hour of operation. Diesels needed 0.3 of an hour. Steam locomotives required water, coal, ash removal, boiler washing, and dozens of daily inspections. Diesels needed fuel and occasional oil changes. The Niagaras were the best argument steam had left, and they still lost. By 1953, all 25 were stored. By 1956, scrapped. Not one survived for preservation. The railroad that had championed steam innovation from the Hudsons through the Niagaras decided the economics could not be argued with. Even the most innovative steam design could not escape the fundamental truth. Steam was simply more expensive to operate than diesel, no matter how well you built it. The Erie Triplex of 1914 was not a 1940s locomotive, but its shadow hung over every experimental steam design that followed. It was the cautionary tale that innovators should have heeded. The 2-8-8-8 wheel arrangement had 3 sets of driving wheels, including 1 set under the tender, all powered by a single boiler. On paper, it was the most powerful locomotive ever built. In practice, it was a monument to engineering hubris. The boiler simply could not make enough steam for all 3 engine sets. When starting, the triplex could move anything. Above 15 miles per hour, steam pressure collapsed. The rear engine set under the tender starved first, then the middle set. Engineers called it the yard ripper because it could drag immense tonnage out of terminals but could not maintain speed to the next town. What makes this relevant to the 1940s failures is simple. Designers kept ignoring the triplex lesson. The turbine experiments failed because boilers could not keep up with turbine demands. The duplex locomotives slipped because dividing power created coordination problems. The high-pressure experiments failed because complexity overwhelmed reliability. Every innovative steam locomotive of the 1940s repeated some version of the triplex's fundamental error, assuming that more power automatically meant better performance. It never did. Number 1. Pennsylvania Railroad's entire duplex program. The ultimate failure was not a single locomotive. It was an entire philosophy. Between 1937 and 1946, the Pennsylvania Railroad invested millions in duplex technology, the S1, Q1, Q2, S2, and T1. They built 80 duplex locomotives in total. By 1953, every single one was scrapped. Not one survived for preservation. The program failed because the Pennsylvania Railroad mistook complexity for progress. Each duplex solved one problem while creating 3 more. The S1 was too long. The Q1 had backward cylinders that overheated. The Q2 cost too much to maintain. The S2's turbine could not handle variable speeds. The T1 slipped uncontrollably. These locomotives consumed resources that could have improved conventional designs. They diverted attention from dieselization until it was too late. They created maintenance nightmares that accelerated steam's decline. The Pennsylvania Railroad went from industry leader to a cautionary tale. Competitors adopted diesel power while the Pennsylvania Railroad chased innovations that never panned out. The railroad's post-war decline was partly caused by betting everything on technology that could not deliver. When the Pennsylvania Railroad merged into Penn Central in 1968, decades of poor decisions had hollowed out the company. The duplexes were gone, but their legacy of failure remained. And that's all, folks. These locomotives prove that innovation without reliability is just expensive failure. If you enjoyed this journey through steam's most ambitious disasters, hit subscribe for more railway history. Watch another video I specially selected for you. See you next time.